In this video, we're going to be solving some kinematic projectile motion problems, starting off with 1.1. A ball is launched from ground level with an initial speed of v initial at an angle theta above the horizontal. After 2.0 seconds, the ball is 12 meters horizontally from the launch point and 6 meters above it. Find the magnitude of the initial velocity and the launch angle. So, what we can do is first we can split into components. And what this means is we can target the horizontal and the vertical. So for the horizontal, we have x is going to be equal to v initial x times t. And this is going to be 12, which is here. And we have our v initial, which is going to be our unknown. And we have cosine of theta 2.0. So that is going to be equal to, this is going to be for v initial cosine theta is equal to 6. So now we have that y is equal to v initial yt minus 1/2 gt squared for our vertical direction. And here we have 6 is equal to v initial sine of theta 2.0 minus 1/2 9.8 2.0 squared. And then this is going to be equal to 6 to v initial sine theta minus 19.6. This is going to be v initial sine theta is equal to 12.8. Now, if we solve for v initial, this is going to be equal to 6 squared plus 12.8 squared. And this is because v initial is equal to the root of v ox squared plus v oy squared. And these are the same thing as these values here. Vos y sine theta, that's this. And then this is going to be cosine theta, that is just this. So now after this, if you plug this into your calculator, you're going to get 14.1 meters per second as your v initial. And we need the angle, because when you report this, you need both the velocity and you also need the angle that it is launched at. So your angle, you're going to find that tan negative 1 of v initial y over v ox. That's just going to be tan negative 1 of 12.8 over 6. And that's going to be 16.5. And this is going to be, this was our VOY, and this was our VOX. And yes, this is 65. Now, let's move on to our next question. A projectile is launched. At one point, its velocity vector makes a 30-degree angle below the horizontal. Is it possible for this to occur at the launch point? Explain mathematically. So we know that at launch, this point, which is a velocity vector, it can be represented as v initial cosine theta, v initial sine theta. And we know that for a downward angle, that vy is going to be negative. So this means that, but we also know that initially, that v initial y is going to be equal to v initial sine theta. That's just what the formula is. And then we know that this is going to be positive. And we know that this doesn't make sense. So that this is impossible, because something can't be positive and negative at the same time. So think we just have our guy here. He's throwing something. At this point, it has both a vertical and a horizontal component, and it cannot be both positive and negative at once. So what we know is that downward angles only occur after passing the peak when gravity reverses the sine of Vy. And that's because we can see here, this is when Vy is equal to 0. So as we know, like on all these points, you're going up still. Maybe not that here. You're still going up, but then when you're going here, once you've switched, you're now going down. And your angle is going to be, your angle is here. That's your angle. But now your angle is negative. A projectile is launched with a speed of 20 meters per second. At a point 15 meters above the launch height, its speed is measured to be 10 meters per second. Determine the launch of the projectile. Okay, so for this, we can use vertical motion, but we are not given time. So because we're not given time, we use the equation that doesn't incorporate time, which is v squared is equal to v initial of y squared plus 2 times alpha times delta y. And we can write this as 10 sine of theta squared is equal to 20 sine of theta. We can actually make this a different angle squared. Minus 2 times 9.8, and delta y, that is 15. But we know that horizontal velocity is constant, and because we know it's constant, we can say that v of x is equal to 20 cosine theta, and then we know that that is equal to 10 cosine of the other angle. So now we can rewrite this as cosine of the other angle is equal to 2 of cosine of theta. And now we can use the identity that from trig we know that sine squared of an angle is equal to 1 minus 4 cosine squared of theta, right? So then if we plug this in, we can solve 100 times 1 minus 4 of cosine squared theta. That's going to equal to 400 sine squared theta minus 294. So then theta is going to equal to 53.1 degrees. A projectile passes through the vertical height twice during its motion. The same vertical height twice during its motion. At one point, its speed is 18 meters per second, and the other is 10 meters per second. Explain how this is possible and determine which speed occurs first. Well, we know that if you have a projectile motion like this, it's going to have the same height twice because it has to go up and it has to go down, and it'll cross right back through it. So we know that at the same height, v of x is going to be constant. This is constant for the whole entire projectile. And we know that Vy will change signs because one has to be positive velocity, one has to be negative velocity, split here. And we know that our speed is represented as v is equal to vx squared plus vy squared. And we know that on the way up, that we can write vy is going to be larger. So you have a larger speed. Now on the way down, we know that our vy is going to be smaller. So you're going to have a smaller speed when you, and this is when you plug these values into this expression. So that means that 18 meters per second occurs first because 18 is greater than 10. A projectile is launched horizontally from the edge of a cliff. It lands on the ground 4 seconds later at a horizontal distance of 60 meters from the base of the cliff. Determine the height of the cliff. So, we know that using horizontal motion, that v initial x is equal to 60 over 4.0. So that is just going to be 15. And we know if we tackle the vertical motion, we have y is equal to v initial yt minus 1/2 gt squared. However, we know that v initial y is equal to 0 because it's a horizontal launch. And because it's a horizontal launch, we can write this as y is equal to negative 1/2 9.8 times 4.0 squared. That is going to be equal to, y is equal to negative 78.4. So height is going to be equal to 78.4 meters. And height has to be positive. So that's why we can just infer that it's 78.4 meters. And the reason why it was negative was because of because of gravity. And okay, and also because of the equation, but that should cancel out. But it's fine. Okay, so a horizontal, yeah, it did. But it's just because we chose that to be down. So a projectile is launched at an angle of 30 degrees above the horizontal. So it's launched 30 degrees, and at the highest point, it's momentarily at rest. What is the magnitude of the acceleration at this point? And explain your reasoning. Okay, so we know that acceleration is always going to be gravity. Always. So that means that velocity being 0 does not mean acceleration is 0. That's because acceleration is the change of velocity over time, and velocity is the change in x over time. And just because the velocity is equal to 0 does not mean the acceleration is equal to 0, because the acceleration is always going to be 9.8 meters per second squared. And the change in the velocity is always going to be equal to the change in, is just always going to be equal to 9.8 meters per second squared. So just because the velocity is 0 doesn't mean that the acceleration is 0. So a projectile is launched from the top of a cliff of 20 meters above the ground with a fixed launch speed. Determine whether the launch angle that produces the maximum horizontal range is greater than, less than, or equal to 45 degrees. So this is kind of tricky. But we know that the max angle is not 45 degrees when your launch and landing heights differ. And the correct condition is that tangent of theta is equal to v initial divided by v initial squared plus 2gh. So therefore, we can conclude that theta is less than 45 degrees. Now, let's see here. We have a v initial of, okay, yes. Okay, a projectile is launched from a cliff 20 meters above the ground with an initial speed of 25 meters per second. Calculate the launch angle that results in the maximum horizontal range. So, v initial is 25 meters per second. your height is going to be 20 meters. And because of this, we can write tangent of theta is equal to tangent -1. This is our formula over here. Might as well just copy that over. -1 of 25 divided by the root of 25 squared plus 9.8 is 20. And that means your theta is going to be equal to 38.7 degrees. A projectile is launched from the top of a cliff with a speed of 15 meters per second at an angle of 45 degrees above the horizontal. It lands on the ground 3 seconds later. Determine the height of the cliff. So this means that we have to use how our formula that relates height. So we have v initial yt minus 1/2 gt squared. We can solve for we have v initial y, that's going to be equal to 15 sine 45 degrees, and that's going to go to 10.6. Subbing this back in, we have our y is equal to 10.6 times 3.0 minus 4.9 times 3.0 for our t squared, and this is going to simplify down to negative 12.9. So that means our height has to be positive, right? So then we have height is going to be 12.9 meters. A projectile is launched horizontally from an unknown height above the ground. The time of flight and the initial vertical velocity are known. Explain why the height of the cliff can be uniquely determined using only vertical motion equations. So, for this, we know that if the time of flight is known and v initial y is known, well, we can prove this because vertical equation contains only those quantities. So you can use a kinematics equation that involves all these quantities to define the height. A projectile lands on the ground with a speed of 25 meters per second at an angle of 60 degrees below the horizontal. Determine the total flight of the projectile. So we can find the vertical velocity, Vy, which is negative 25 sine 60 degrees from v initial sine theta. So now Vy is equal to v initial y minus gt. We can get that solving for t, we have v initial y minus vy divided by g. A projectile is launched toward the ground level. A projectile is launched upward from ground level and lands back on the ground with a greater speed than its launch speed. Explain how this is possible using kinematics concepts. Well, gravitational potential energy converts to kinetic. Well, that's because if it's launched upward from the ground level and launches back down onto the ground with a greater speed, well, that's because initially, we have FG that's always acting down on it at every single point, right? Every single point FG is acting down on it. Here you have maximum potential energy. You have potential energy, right? And you have down here, you have kinetic energy again. And here you had kinetic energy. And because gravity is acting down, it's actually going to give it more speed because now it's being pushed down with the force of 9.8 meters per second squared. So that's added. And a projectile launched from the ground lands 80 meters away. The maximum height reached by the projectile is 20 meters. Determine the magnitude of the initial velocity of the projectile. So the range is going to be 80 meters. And the maximum height, that's going to be equal to 20 meters. So V initial Y, that's going to be equal to the root of 2GH. And that is going to be equal to, our height is 2 root of 2 times 9.8, height of 19.8. Now T is going to be equal to 2 V initial Y divided by G. That's going to be T 2 times V initial of Y. Let's see here. Well, this is going to be equal to 4.04. So the time is equal to 4.04 seconds, right? So now we can write that V initial X is equal to 80 over 4.04, and that is equal to 19.8. And we know V initial is going to be equal to the square root of the differences between these two v's. It's just Vx squared minus Vy squared. So then we can write that we have the square root of 19.8 squared plus 19.8 squared, and then that is going to be equal to 28.0. Two different projectiles are launched from ground level with the same initial speed, but at different angles. Show that the two different launch angles can result in the same horizontal range. Okay, so let's start off with the principles of what range means. So range is the horizontal distance traveled, right? So that's just R is equal to Vxt. So in order to find the range, we need the horizontal velocity Vx and also the time t. And we know that from a projectile launched from the angle of V initial at an angle theta, right? We have Vx is equal to V initial times cosine of theta. And then this is going to stay constant for the entire motion. Right? So then because of this, now from here we can determine the time of flight. So in order to find the time of flight, we have to look at the vertical motion, which is how long is the projectile in the air, right? So that's just the vertical velocity Vy, which is equal to V initial times sine theta minus gravity times time. And then at landing, Vy is gonna be equal to negative V initial sine theta. So then if we solve for time, then we have time is equal to T2 times V initial times sine theta divided by G. Now that we have time, right, we can substitute this into the range formula. So we can take this and put this right here. So then after we do that, we have that R is going to be equal to V initial times cosine of theta times 2 times V initial times sine of theta divided by G. And then if we simplify this down, that we have R is equal to 2 times V initial squared divided by 2 times sine theta times cosine of theta. And then we can use a trig identity. Hopefully you should be in at least pre-calc in AP Physics 1. But we know that sine 2 of theta is equal to 2 sine theta cosine of theta. And if you substitute this in, then you have that R is going to be equal to V initial squared divided by G sine 2 theta. Because we see right here, we can see the identity sine. Okay. See sine theta 2, right? That's this. Sub that in right there, right? So then we know that from the sine function, we know that sine function, it has symmetry, and that is that sine of an angle, right, is equal to sine of 180 degrees minus the angle. Now if we apply this to 2 theta, right, we have sine 2 theta is equal to sine 180 degrees minus 2 of theta. So then you have that 2 theta is there, and you have 180 minus 2 theta, and then that's going to be, they're going to produce the same range, right? Because those are both inputs to the angle. They're both inputs. And they are both inputs to sine, and then that will produce the same output. So now, if you divide by 2 for both of these, actually, let me move this, have room. Okay. Okay, now if you divide both of these, right, by 2, then we have theta and 90 degrees minus theta. So that's going to be our 2 answers, which was also written over here, but yes. So that means that 2 different launch angles, theta and 90 degrees minus theta, they produce the same range because the range depends on, it depends on sine to theta, which has the same value for those two angles. And the reason why this makes sense is that if you have a lower angle, that means you have a larger horizontal speed, and that's going to equal a small time in the air. But if you have a higher angle, that is going to be a small horizontal speed. That's going to equal to a large time in air. Now let's move on to our next question. A projectile is launched parallel to the surface of an inclined plane. Demonstrate that the projectile lands at the same vertical height from which it was launched relative to the plane. So, well, we can let's draw the inclined plane, and we're going to let the inclined plane angle equal to this angle alpha. And then the launch direction, is going to be parallel to the incline. Now, our coordinate axes, our y is going to be perpendicular to the plane, and then the x is going to be along the line. So that's going to be parallel to this. And then if we can resolve the gravity into inclined components. Well, so let's just say like FG is like this, right? So then if we have this, okay, say like we have FG on like a point, right? So we have FG. We can break FG up, and then that's going to be like this. We're going to have, for our x, we're going to have G sine alpha, and for our y we have G cosine alpha. And then we have for our initial velocity, we have v initial y, that's going to equal to 0, and that's because the launch is parallel to the incline. And then we can do the motion that is perpendicular to the incline, and the motion that's perpendicular to the incline, we can use kinematics, and you can use the y is equal to v initial yt minus 1/2 ay t squared. And then if you substitute in what we just got for that, we have y is equal to negative 1/2 g cosine alpha t squared. And yeah, that was just cosine here, ay g cosine a, yes. And now, okay, so now we can ask, like, so when we're now curious, like, when does the projectile hit the incline again? And we know, like, that the projectile is going to land when its y prime is equal to 0. That's when it lands, right? Land. So it would be launched from like this. and our height of 0 is relative to the incline. So basically, just like think of it, it's just like this is just a flat surface, but we just have gravity that goes down because it's at an angle, right? Now that's gonna happen at it's gonna land at t is equal to 0, and also t is equal to a non-zero number, right? And we also know that the motion is gonna be symmetric in time. So the projectile returns to the same perpendicular distance from the plane. Which means they have the same vertical height relative to the incline. So again, because the projectile has zero initial velocity perpendicular to the incline and experiences a constant acceleration in that direction. It returns the same perpendicular displacement. So returns same perpendicular displacement. It returns the same perpendicular, but we already wrote that there. Same perpendicular displacement, which means it's at the same height relative to the incline. Okay. A projectile is launched with a speed v initial at an angle theta above the horizontal onto an inclined plane that makes an angle alpha with the horizontal. Determine an expression for the time of flight in terms of v initial, theta, and alpha. Okay, so we know that for the initial velocity that's perpendicular to the plane, to the incline, we have the incline here, alpha again, to the incline. We can write v initial y is going to equal to v initial sine theta minus alpha. Now for the acceleration that is perpendicular to the incline, we have ay is equal to g cosine of alpha. Now if you use the perpendicular motion equation, we have y prime is equal to v initial y prime t minus 1/2 ay prime t squared. And we know that the projectile, it's going to land when you have y prime is equal to 0. So then you're going to have 0 is equal to v initial sine theta minus alpha t minus 1/2 g cosine alpha t squared. Now after this, you can factor and solve. So we see that we have t here, right? So we can just rewrite this. This is v. So we can rewrite this as t of v initial sine theta minus alpha minus 1/2 g cosine alpha t. We have an extra t there. It's equal to 0. So now we have, for just solving for t, we have t is equal to 2 v initial sine theta minus alpha divided by g cosine alpha. Okay. Now, let me make this a little bit neater, but yes. Now, after this, let's see here. A projectile is launched from the ground level with initial speed of v initial. Derive the expression for the horizontal range and determine the launch angle that maximizes the range. Okay, so we know that range, which we also previously seen, r is going to equal to v initial squared over g sine 2 theta. And we know that it's going to be max when sine 2 theta is equal to 1, right? And that's going to be, we can think of this as just the input, right? So if you have sine of 90 degrees, that's going to equal to 1, right? So that means that theta is going to equal to 45 degrees since it's being multiplied by 2. That's your answer. In the presence of air resistance, the launch angle that produces the maximum range is less than 45 degrees. Explain why air resistance changes the optimal launch range. Well, that's because horizontal velocity decays faster. In addition, we also know that the horizontal velocity, it stays constant. And we also know that vertical motion only affects time in the air, right? And we know that range is maximized when horizontal distance covered per unit of time and the total time in air are balanced, which happens at 45 degrees. So you can imagine you have like this 45 degrees. So that's going to be perfect. So this is perfect symmetry between the horizontal and the vertical motion. So now we have to identify when air resistance will change, how air resistance will change this optimal range. So if we have air resistance presence, we know that air resistance, it introduces a force that always acts opposite the velocity. And it also reduces the magnitude of the velocity. And it also depends on how fast the object is moving. Right? And most importantly, what does this mean? This means that Vx is no longer constant. And that means mechanical energy is no longer conserved, since that's an external force. Longer conserved. And this breaks the 45 degrees optimal. Now, if we focus on the horizontal motion, right? So if we know, for horizontal motion, we know that our range is going to be equal to the integral under Vx t dt. And we know that with air resistance, that Vx will continuously decrease. And we know that the longer the projectile is in the air, right? And so then that means that time in air is bad. It's a disadvantage. So now we can see that. So you can imagine that the high launch angle, which is approximately 45 degrees or greater than 45 degrees. So greater than or equal to 45 degrees. That means that you have a large vertical velocity, you have a large Vy, and you have a long time in air, and that means that your horizontal velocity has more time to decay, and that means that the projectile hangs while losing. So that means that the projectile hangs like in the sky, it's flying while losing horizontal speed. Now, on the other hand, for a lower launch angle, right, that is below 45 degrees, that means that you have a smaller Vy, you have a shorter flight time, and you have less time to reduce Vx. So that means you're going to have a greater horizontal distance, and for a high launch angle, you're going to have a shorter range than expected. So look, more time in the air, there's going to be more time for it to decay. But if it is a lower launch angle, it's going to go further because it's going to have less decay. So the reason why the optimal angle must be less than 45 degrees is because we want to preserve the horizontal velocity as much as possible, and we want to minimize the time spent losing speed to drag. Losing speed to drag. So this favors the horizontal motion. And this decreases the vertical loft. So again, the optimal angle will be below 45 degrees. And we can actually prove this using some physics equations. So we have with air resistance. Okay, so again, we know that range is going to be equal to the average horizontal velocity, Vx, times the time of flight, right? Now, what happens when there's air resistance? So if you have air resistance, right, that means that there's a horizontal force. That means that your summation of the horizontal forces is not going to be equal to 0. It's not going to be canceling out. So therefore, by Newton's second law, with the summation of the horizontal forces equal to mass times the acceleration in the horizontal direction, that means that a of x is not going to ax, your horizontal acceleration, is not going to equal to 0. So this is the first difference from ideal projectile motion. So then we can use the kinematics equation in the x direction, which is Vx is equal to V initial x plus AXT. So with air resistance, this makes A of x negative, right? And then that's because drag opposes motion. So that means that V of x has to be less than V initial x, and it will decrease with time. So Vx is not constant. Now we can compare these high and low angles using equations. So by using equations, we can represent high angle, we can represent the horizontal angle with VOX is equal to V initial cosine theta, VOY is equal to VO sine theta. So using that, we can write this out for both of these situations. So high launch angle, we have that you have a smaller VOX and you have a larger VOY. You have longer T, right? But for lower, you have a larger VOX, you have a smaller VOY, and a shorter time of flight T. Right? So using the same equation, V initial, Vx is equal to Vox plus AXT. So that means that you have a longer T. That means you have a larger reduction in T, or in Vx. However, a shorter T means a smaller reduction in Vx. And if you connect this back to the range, right, we know, okay, so we know that range is this. So that means at high angles that you have a long T but a very small average Vx, and at lower angles you have a shorter V but a much larger average Vx. And that's because air resistance reduces Vx, preserving the horizontal speed, more important than staying in the air longer. So